Okay, today I'm going to be looking at one aspect of the A-level maths course in mechanics, particularly Newton's laws, and looking at connected particle problems, specifically looking at lift problems of people going up and down in lifts. So let's look to begin with at the model. So I've modelled the lift very simply as a box that's suspended by a cable, and I've put the person in the lift, and we're going to look at the forces that are acting on this system. So the first thing is that the person would have a mass, so let's say that that's m1, which means that there will be a force acting down on the lift of m1g, the weight of the person. The lift would have a mass m2, so there will be a force downwards due to the lift of m2g. And what's holding this up is the tension in the lift cable. So we'll put a tension going vertically upwards in the lift cable. So with the person in the lift, those are the three forces. Now I'm also going to look at the forces on the individual components, the individual person and the individual lift. So I'm going to look at the person and the lift. So if we look at the person, well, we've just said that there'll be a force downwards on the person, which is their weight, and we called the mass m1, so their weight is m1g. And we said that the force on the lift was a force downwards of m2g, the weight of the lift. We also said that there'd be a tension in the lift cable going up. So hopefully you can see that at the moment I've got the forces on the person and the lift. If I put the person into the lift, I would get the diagram on the left hand side. However, there's another force that acts on the person, because the person at the moment would be accelerating downwards because there's only one force downwards. There's a force up acting on the person, which is due to the floor of the lift, which is the reaction. And it's the reaction through the soles of your feet that you feel. That's the force that you feel when you're standing in a lift, or when the lift is travelling upwards or downwards. Now, I'm just going to draw a little dividing line down there, because at the moment we've got the whole system on the left, and we've got the person plus the lift on the right. Now, if you put the person into the lift, you can see that we would need to also have a force downwards acting on the lift, which is equal and opposite to the reaction on the person. So when I put the person into the lift, when I add them in, the reactions would then cancel out, because one force would be vertically up, one force would be vertically downwards, and we would have the three forces here: the weight of the person, the weight of the lift, and the tension. Now, in these problems, at times it's easier to consider the whole system, so what we've got on the left, if I'm trying to find the tension, for example. And at other times we've got to consider the particles separately. We've got to consider the person, forces on the person, or we've got to consider forces on the lift separately. Okay, so that's what we're going to do in the next couple of slides. So if a person of mass 70 kg is in a lift of mass 600 kg, which is accelerating upwards at 3 meters per second squared, we're going to find the tension in the lift cable and the reaction of the lift on the person. So to begin with, I'm going to find the tension in the lift cable. Now, in order to do this, it's easiest if we consider the whole system. So this is with the person standing in the lift. So the forces downwards, as in the previous slide, are the weight of the person, 70g, and the weight of the lift, 600g. So by Newton 2, we are accelerating upwards at 3 meters per second squared. So Newton 2, the resultant force is the mass times the acceleration. So we're accelerating upwards, so the resultant force upwards is T, is the only force upwards. I've then got to take 70g and I've got to take 600g because those forces act downwards. So accelerating upwards, the direction of the acceleration, I'm going to take positive acceleration upwards, so the resultant force upwards is T, take 670g. So this equals the total mass, now this is 670, times the acceleration, 3. So that's Newton's second law. The resultant force is the mass times the acceleration. And we can calculate the tension. So T take 670g is 670 times 3. So the tension will be 670 times 3. I'm going to add the 670g to get the tension, and that comes out to be 8576 newtons. Now critically, because we have used G, here it is, because we've used G in the question, you've got to give your final answer to 2 significant figures. So that will be 8,600 newtons. So 8,600 newtons in the lift cable is the tension. Now, if we're going to find the reaction of the lift on the person, I just want to look at the person. So if we look at the forces on the person, well, the forces on the person are the weight of the person, 70g, and the reaction of the floor of the lift on the person will be upwards r, and the person's in the lift, so they're accelerating upwards at 3 meters per second squared. So we can use Newton 2 on the person now. So the resultant force upwards is r take 70g, and this is the mass, which is 70, times acceleration, which is 3. So if we rearrange this, r is 70 times 3 plus 70g, and that comes out to be 896 newtons. So again, I'm going to round that to 2 significant figures, which is 900 newtons, because I've used G is 9.8. So the reaction on the person is 900 newtons, and the tension in the lift cable is 8,600 newtons. Now note, if the lift was stationary, the reaction would be 70g, and this line here shows you that the reaction is a little bit more than 70g. It's 70g plus 210. So the force that this person's feeling through the soles of their feet when the acceleration is up at 3 meters per second squared is more than their normal weight if they were stationary. So when you accelerate up in a lift, that's why you feel slightly heavier. Okay, so what happens when we are now accelerating downwards? So if a person of mass 70 kg is standing in the same lift of mass 600 kg, but this time it's accelerating downwards at 2 meters per second squared, we're going to find the tension in the lift cable. So same as last time, I'm going to put the person into the lift and look at the total forces. So the weight of the person, the weight of the lift, they act downwards, and the tension acting upwards. I'm going to call it T1 because we're different from the T that we had last time. And we're accelerating this time downwards at 2 meters per second squared. So Newton's second law. Now I'm accelerating downwards, so I want the resultant force downwards, which is 70g plus 600g, because they both act downwards. Take T1 is the total mass, 670 times the acceleration, which is 2. So this time I'm taking the positive direction downwards. So let's work it out. 670g take T1 is 670 times 2. So I can add T1 and take the 670 times 2. So 670g take 670 times 2 is T1. And if we plug that into the calculator, that comes out to be 5226 newtons. So we're going to again round it to two significant figures, which is sorry, just get rid of that, which is 5,200 newtons. The reaction of the lift on the person. So now we are looking at the forces just on the person, which are the weight, 70g, the reaction, R1, and the person inside the lift is accelerating downwards at 2 meters per second squared. So Newton's second law, the resultant force downwards is the force down, take the force up, and this is the mass times the acceleration. So let's rearrange it again. And if we work that out, the reaction comes to be 546 newtons. So two significant figures is 550 newtons. And again, if you look at this line here, if the lift was stationary, the reaction would be 70g. The person would feel their mass 70 times g, 9.8. They would feel that as their weight. But you can see here that they are 70 times 2 newtons less than 70g. So they feel lighter. So when the lift accelerates downwards, they feel slightly lighter than they did when they are stationary. Okay, thank you very much for listening.